Hi there, my name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and I'm in the lab that my colleague Alan Robinson uses for his audio engineering class, and my colleague Brian Beck uses for his telecommunications laboratory class. They're kindly letting me use it for my guitar amplification and effects class. A couple of years ago, I did some labs where we used these bench supplies, but we were obviously limited in the amount of voltage we could use. I went through a storage room that the lab techs use and found this old 60-volt power supply. And I found a couple of these old 50-volt power supplies in Marshall Leach's old lab. I figured that this way we'll at least be on the published operating curves of the tube, and at this voltage, I don't have to worry about the students turning themselves into electro. I'm using a 12AX7. There's tubes that would be much more appropriate for a lower voltage application than the 12AX7. I'm using the 12AX7 because I happen to have a stack of them, and the students have been doing homework problems with the 12AX7 all semester. So I thought it'd be cool for them to actually get to use one in person. I zoomed in on the output characteristic curves of the 12AX7. The lines here correspond to grid cathode voltages of 0 volts, minus 0.5 volts, and minus 1 volts. I placed 1 point down here at 50 volts, so that's our B plus supply as they call it. Here I'm calling that VPP. And then I just sort of played around with rubber banding this line in PowerPoint, and I noticed that I could set an operating point here at the VGK equals minus 0.5 volt line. And then I could get a swing of 0.5 volts one direction and 0.5 volts the other direction at the input. And that would correspond to a swing of 20 volts one direction and 20 volts the other direction at the output. So swing 20 volts to the right before you hit the power supply, and then a swing of 20 volts to the left before you hit this VGK equals 0 line. So I thought that might be fun. The equation shown here is what we use to figure out what's going on for this point on the left. Here we're assuming that all of the power supply voltage is dropping across the resistors. And of course, usually the load resistance is a lot bigger than the cathode resistance, so we'll make this usual kind of approximation. So plugging in 50 volts and this 0.6 milliamp here, I wound up with a resistance of 83.3K, which I just rounded to 82K as a standard resistor value. Then to choose the cathode resistance for our appropriate bias point, I plugged in minus 0.5 for VGK for our bias point, and then I divided it by this 0.25 milliamps, which is where this point intersected here. And I wound up with 2K, which when I built it, I just rounded that to 2.2K to get a standard resistor value. If you look at the parameter curves here, 0.25 milliamps. Let's see, maybe, I'm just going to go ahead and say mu equals 100. It's probably less than that, but whatever. And what should we say the dynamic plate resistance is? Well, let's see, extrapolating this, maybe 150K? I don't know. Remember that these characteristic curves are drawn for a plate voltage of 250 volts, which we're nowhere near. So I have no idea how accurate any of this is. Okay, so I've claimed that a swing of 0.5 volts at the input will give us a swing of 20 volts at the output, giving me a large signal gain of 40. And if I use my usual small signal gain formula, I'm assuming that this is all completely bypassed. Let's see, we have mu, RL, and RP, and plugging in those numbers and I get 35. Okay, here we go. So the yellow line is the input, and the green line is the output. It's inverting as you would expect. Running 50 volts for our plate supply. And I'm using this supply over here to create the 12.6 volt filament voltage. And at least according to the web searches, 150 millivolts seems appropriate for that. I'm putting in an 82 hertz wave. I think that's a low E if I remember correctly. 1 volt peak to peak, One thing I have to always remind myself is that you have to go into this menu here, select output load, and make sure this is set to high Z. If you have this set to 50 ohm, then all of the output is double what you think it should be. For instance, if I set this to 50 ohm, right now you'll see it change to 500 millivolt. Okay, so let me set that back to the high Z. There we go. So I have the filament voltage supply here. I have a 1 mega ohm resistor going from the grid to the ground to provide a reference. I have a 2.2K resistor going from the cathode to ground. And then I have a 82K resistor coming from my B plus voltage supply, I guess you could call it, to the plate. And then I'm measuring the output at the plate here. Notice I don't have a DC blocking capacitor here, so I'm relying on the AC coupling mode on my scope because I was feeling lazy. One thing to watch out for is if you hit the auto scale button on this particular scope, it sets the coupling back to DC. And then I have the input from the signal generator coming into the grid. So I was targeting a bias voltage of 30 volts DC at the plate, and that's reading 36, so higher than I was expecting, at least based on those graphs. Who knows how accurate those graphs are down at that lower voltage. Now I'm going to look at the bias voltage at the cathode. That's reading around 0.35 volts, which gives me a grid-to-cathode voltage of minus 0.35 volts. And I was targeting minus 0.5 volts. But again, who knows how accurate those grid lines are. Let's say I have a peak-to-peak voltage going in of 1 volt and peak-to-peak voltage of 16 volts coming out. Let's see, that's a large signal gain of 16. I was expecting something more like 40. Okay, now what I'm going to do is I'm going to start cranking up the input and see where the output looks like it starts to round out. It looks like it's starting to distort on the top end of the output. I'm at 1.7 volt peak to peak now. Let's keep going. Okay, this is 2 volts, definitely rounding on the top end. Here's 2.5 volts. Let me crank down the scale here. Oh, that's at the limit, it says. Anyway, let's keep going. 3.5 volts peak to peak. Let me scoosh this up just so we can see it. Yeah, it's definitely rounding. Starting to do something down here, but it's still pretty sharp. But it's definitely starting to flatten out up here. That's for 3.7 volts peak to peak in. Here's 4 volts peak to peak in. So if you just naively read this, you would say the large signal gain is 10. But of course, it's really flattening out up here. You know what might be fun? Let me grab a breadboard and we could replace this cathode resistance with a resistor and a pot in series and maybe play around with different bias points. Okay, so now I have a resistor. This is a 500 ohm resistor in series with a 10K pot. And as I turn that, wow, that's a big difference in gain. Oh, wait a minute. I forgot something. I did something dumb. You see it? I forgot the cathode bypass capacitor. So when I turn up the cathode resistance, I'm getting cathode degeneration. Okay, let me go get a capacitor. I turned off the power supply so I could measure the resistance across this resistor pot setup. And I set it to 2.2K, so that should more or less correspond to the fixed resistor I had earlier. So my resistance across the resistor in the pot now reads 2.2K, and I put in a 22 microfarad bypass cap. Let me disconnect my ohm meter here. Okay, so my DC bias voltage on the plate is a little bit higher than 36 volts. Let's see, it looks like I have a large signal gain of around 28, but let's see, it is rounding off a little bit on one end. Okay, now I'm going to try twiddling that trim pod. See what that does. That does that. Let's go the other way. Oh, looks like it's just better all the way up like that. So let me double check and measure what's going on here. Okay, so this is showing 44 volts DC as my plate bias voltage. And this means my grid to cathode bias voltage is something like minus 700 millivolts. So this is cold biasing, like on one of the Mesa Boogie stages where it's designed to distort on purpose. Okay, let me crank it the other direction. So if the potentiometer swung the other way, that's giving me a plate bias voltage of around 30 volts. And now I'm measuring a voltage at the cathode of 150 millivolts. So that's a grid to cathode voltage of minus 150 millivolts. So I don't understand quite why this is working so well. Seems to me it should be clipping on the other end. Anyway, that's giving me a large signal gain of 33. And that's with this 500 ohm cathode resistance. Okay, let's go nuts. What if I replace this 500 ohm with a 100 ohm? This doesn't make sense to me. Okay, with that 100 ohm resistor, I'm getting a large signal gain of 33. My plate DC voltage is 25 volts. Now here's the thing I don't understand. My grid to cathode bias voltage is minus 35 millivolts. So why does this output look so good? What? That grid to cathode voltage is going positive, and I thought that tubes didn't like that. Somebody can help me understand what's going on. Please leave a comment below.